este semestre. Hoy tenemos el gusto de tener con nosotros a Damien Gaboriau, de la Escuela Normal Superior de Lyon, en Francia, y nos va a hablar en inglés on the non-vanishing of the L2 homology of out and out in top dimensions. Muchas gracias, Damien, por estar aquí.
Muchas gracias. Disculpe, no puedo hablar en español. Solo unas palabras, pero... Okay, so, on the non-vanishing of the L2 homology of hot Fn and ut Fn in top dimension. First of all, you are not supposed to understand all the words in the title. And my goal will be to essentially explain them and give you an idea of the result behind this mysterious title, maybe. So first of all, Fn is the free group on n generators. Let's say Fn is generated by x1, xn. Hot, so this is a group. Hot Fn is the group of automorphisms of this group. So you know that when you have a group, among the automorphisms, you have the inner automorphisms. Those consist in multiplying each element by, say, gamma inverse. Okay, these are called the inner automorphisms. And this is a normal subgroup in hot, so that you can divide out, and what you get is the group of outer automorphisms. Okay? So this explains the two groups appearing in my title, hot Fn and ut Fn. So first of all, I will give you an example of some elements in hot Fn. So, in order to produce an element in hot Fn, you just need to explain where you send the automorphisms and convince yourself that what you get is again a basis of your group. Okay? So, my first example is the following. You send x1 to x1 itself. Then you send x2, 2, and you pick a certain element, or let's say x1 to the L1, x2. Okay? You can also multiply by a power of x1 on the right, L or left, right. Okay? Maybe with a minus just for some consistency. x3, you can send it to x1, L2, x3, and multiply by x1 minus or 3. Sorry. Oh, let me change the notation. 2, 2, 3. Xn sent to x1 to the Ln, xn, x1 to the minus Rn. Okay? So, for each choice of the Li and Ri, I get an automorphism. You can observe that this way I defined an abelian subgroup. Multiplying on the left or on the right are commuting operations, and multiplying this generator or that generator also give commuting operations. Okay? This way, I embedded Z to the 2n minus for (1 minus 2) inside hot Fn. Right? What about out Fn? Here, observe that if you put all the Li equal to 1 and all the Ri equal to 1, you get an inner automorphism. Okay? So for this reason, it's enough, indeed, you can check it easily, to just impose the first L2 to be trivial. Okay? And then you get an outer automorphism. I mean, you get a non-trivial element here. And this way you embed Z to the 2n minus 3 inside out Fn. Okay? Good. Now, I like my phone to remind me when it's almost over. Okay, now let me write the statement so theorem the L2 homology of hot Fn does not vanish in dimension 2n minus 2. This is not unrelated to the 2n minus 2 appearing there. And the same with out Fn does not vanish in dimension 2n minus 3. Okay? Observe that, well, L2 homology, I will explain you what it is, but I will just mention that when it does not vanish, this is witnessed, in some sense, by a number, the L2 Betti number. When you have homology or cohomology, you have usual Betti number. I will redefine you this for you in a moment. And in the L2 context, this is the same thing. So you have, okay, just let me write it, that we have L2 Betti numbers which witness the vanishing or non-vanishing of L2 homology. Okay? Just in this theorem, I'm not able to compute the exact value, just that it does not vanish. Okay? You can believe that L2 Betti numbers vanish if and only if the homology vanish. Okay? Good. So the dimension is not a usual dimension as a vector space. It is. Okay, so I guess this will appear in the discussions. Okay, I can mention that this L2 Betti number, the notation is beta k for the dimension and 2 for L2. And gamma for my favorite group. I should mention that beta 1 of out is 0 for n greater than 3. Oh, just to mention, when n equals 2, ut fn is isomorphic to gln gl2 z. Okay, so it is very particular. It's almost like a free group. Okay, and for higher n, it behaves more like SLNZ. So you have a dichotomy in some sense. Anyway, so this is 0 for n greater than 3, and the second homology vanishes, we know, only for n greater than 5. And this is a common result with Miklos-Chabert. Okay? Just to mention also that maybe you know the notion of Euler characteristic for spaces, for simplicial spaces. Is the alternative sum of number of vertices minus edges plus triangles and so on. You have the same notion for groups. Groups have usual Betti number. I will discuss that. And they have L2 Betti numbers. And you get the same notion. You can alternate the sum. You can take the alternative sum of usual Betti numbers and also of Betti numbers. Okay? And the Euler characteristic is conjectured by Smiley and Voigtman. Okay. Voigtman conjecture that the Euler characteristic is always negative. It has been checked until n equals 100 using computers. Okay? This goes in the same direction. Observe that 2n minus 3 is odd. So if you take the alternative sum, my conjecture indeed is that all the L2 Betti numbers are 0 except the top dimensional one. And all of this goes in the same direction. Okay? Good. I can mention also that with Lord Bartholdi, we try to obtain explicit classes in the homology of groups, of these kinds of groups. First of all, I will tell you a corollary of the result above, which is obtained via the so-called Luc approximation theorem. And this is the following. Let me write that, for large enough finite index subgroups, gamma j of ut fn, the usual Betti number in top dimension is non-zero. And moreover, this grows linearly in the index. It grows linearly. In the index. Okay. So, and this is exactly where we work with Laurent Bartholdi to produce as many classes as possible. So I will, first of all, go to the notion of dimension for groups. Top dimension. What does it mean? Okay. So for instance, if I ask you what is the dimension of Z square, there are two, let's say, canonical answers. One is, well, it is a discrete group. Its dimension is 0. And there is a more geometrical-oriented answer. Z square acts on the plane nicely. Okay? And this is the answer I expect from you. I give you the definition. So, let's say torsion-free. So a group, all of whose elements have infinite order. A torsion-free group, gamma, has geometric dimension n, or d, dimension, if d is the smallest possible dimension of a complex on which the group acts very nicely. I will precise it. Geometric dimension d, if d is the smallest dimension of a simplicial complex, and I want the simplicial complex to be contractible. You know, you can retract it to a point of a contractible free gamma complex. I want the action of gamma to be free on it. Okay? Does it make sense? So for instance, the geometric dimension of Z to the D equals D. Okay? This notion of dimension decreases when you take subgroups. Of course, if you have a subgroup, it acts nicely on the same spaces as the ambient group. Okay? So for instance, if your group gamma contains Z to the D, its geometric dimension is larger than D. So for instance, the dimension of UTFN is greater than, 2n minus 3. Okay? Okay. Now, I will just claim that the dimension of UTFN is exactly 2n minus 3. There is a space introduced by Köhler and Vogtmann in 86, which is called the spine of the outer space. So first of all, they introduce the outer space, the space on which UTFN acts. Okay? And you take the spine of it. So it is a space Kn. It is a simplicial space, simplicial complex. The vertices are pairs, let's say, G, G. Big G is a graph. So it's a finite graph. All its vertices have valency greater than 3, so no valency 2. Okay? And G, well, G is a homotopy equivalence, so it's a map from Rn, which is the rows on n petals. This is for free. Okay? So you have a map from Rn to G, which induces an isomorphism for the fundamental groups. Okay? So these are the vertices, and now a collection G0, G1, and so on, GK spans a K simplex, if and only if you can go from one to the next one by just collapsing a forest in the graph. So for instance, your graph can be something like that. Okay? So this is for n equals 3. I choose, say, this as a forest, and then I can collapse. So for instance, I collapse this forest, so I don't give exactly you can choose any isomorphism to that, then I collapse this forest, this edge, and I get what, something like that, right? And then I collapse this red edge again, and I get the rows. Okay, so this forms a simplex. Okay? A reasonable way, first collapsing this gives another simplex. Okay, so the theorem of Köhler and Volkmann is that Kn is contractible. It is equipped with an action of ut Fn by, well, precomposing here. You see, every element of ut Fn can be realized as a map from the rows to the rows. So you precompose by that. And so this gives you an action of ut Fn on Kn. Simplicial action. And this is co-compact. It is not exactly free, just for a simple reason. Ut Fn admits some finite subgroups. When a group is finite and non-trivial, this is why I put torsion free there. It is quite a stupid thing. The geometric dimension of a finite group would be infinite. But you see, just the action is proper, which means that the stabilizers are finite. Okay? And so this is theorem. But indeed, ut Fn admits a finite index subgroup, which is torsion-free. Okay? So, ut Fn, or a finite index subgroup of it, admits a free action on a space of dimension exactly, what is the dimension? So it is just a simple computation. It is, have a guess, 2n minus 3. Okay? So, let's make an agreement. We will play the, let's believe that ut Fn is torsion-free. Frankly, it's not an issue. Okay? What I tell you is true for finite index subgroups, and everything up to finite index is exactly that. Okay? So, anyway, let me write the virtual, which means up to finite index, a geometric dimension of ut Fn equals 2n minus 3. Okay. No questions so far? This is an Eilenberg, yeah, McLean space, exactly. This is the, okay. Go. Now let me go to a small reminder, let's say, on homology. Okay? Is it okay if I write here? For most of you, maybe not for you, Adolfo. I erase my theorem, it's maybe a mistake, but. Okay, so reminder on homology. So let L be a simplicial complex. Okay. Good. You may know that associated to it, so you have this simplicial complex is made of pieces of dimension 0, of dimension 1, edges, of dimension 2, triangles, dimension 3, tetrahedrons, and so on. Okay? So, associated to a simplicial complex, you have the so-called spaces of chains. So the chains of dimension 0 is just a vector space. It's a vector space with a base made of the simplices of dimension 0. Okay? This is C0 of L. C1 of L is just the vector space, let's say with coefficients in Q or in R. So the vector space with base the one-dimensional vertices, simplices, C2, the base is made of the triangles, and so on. Okay? And we have linear maps between these spaces. So for instance, what is the boundary map from this to that? So if you have one edge like that, let's say an oriented edge, so this one, the other orientation gives you just the opposite vector. What is the boundary? So it's +1 on this vertex and -1 on that vertex. Okay? So what is, just to remind, to make it more clear, what is C1 of L? It is just the collection of formal linear combinations, A sigma, sigma, with A sigma an element of my field, and sigma a one-dimensional simplex. And these are finite sums. Okay? So what is the boundary of a triangle like that? With orientation, this is just the sum of this edge plus that edge. Okay? So once the boundary, the maps are defined on the base, they are defined on the whole vector space, you extend by linearity. Okay? Good. And now, what is called the homology in dimension k. Now this is just, first of all, I should say that, I must say that if you compose twice the boundary, you get 0. Just think in the triangle, bluff, bluff, bluff. The boundary of the triangle is this plus that plus that. But you see that here you have +1 and -1. So that when you compose twice, from here to there, you get 0. Right? And this holds more generally in higher dimensions. And the homology of, say, L is just the kernel of the boundary map dk by the image of the next one. Okay? Since you have the composition being 0, this means that the image belongs to the kernel. Okay? And so this is the homology of the complex L. Okay, its dimension, although my field is just denoted by bk of L, and it is a so-called Betti number. So it's in dimension k, so it's the kth Betti number, the usual Betti number. Okay? Now comes the proposition. Now I consider my first group acting on some k properly, or let's say freely. Okay? Freely and co-compactly, which means that the quotient is compact. Okay? Then I look at hk of k mod gamma. Okay? And the claim is that if k is contractible, then this vector space does not depend on the particular choice of L. So, plus contractible, which is the key property, then this does not depend on L. What does it mean exactly? It means that it becomes an invariant of the group. Sorry, okay. It becomes an invariant of the group. Is it clear? And so the dimension bk of that now is denoted bk of gamma. And you have the definition of the kth L2 Betti number, k Betti number of the group. There are too many k's maybe. Huh? Is it okay? Good. So now, let me mention that the Betti numbers of ut Fn are quite mysterious. Okay? They have been computed precisely for n smaller than 6. They have been computed, and it appears that the top dimensional one for the usual is 0. Okay? For n also greater than 3. I told you that n equals 2 is particular. Okay? So this is due to, excuse me, washi. Okay? Good. Then it has been conjectured by Morita that this should hold for all larger n. And the surprise came with Bartholdi in 2015, when he computed for using computers n equals 7. Just the next one. That, so B11, the top dimension, of ut F7 equals 1. Not 0. Okay. So it remains quite mysterious. Now let me relate the usual Betti numbers with the L2 Betti numbers that I did not define, but I will go in this direction using Luke approximation theorem. It's from 94. So it says the following. You have a gamma, which is so-called residually finite. So it means that in gamma you can find a sequence of finite index subgroups, which is decreasing. The subgroups are normal with trivial intersection. I write it. So you have a sequence, gamma 0, which is equal to gamma 1, gamma 2, such that the index of gamma I in gamma is finite, such that gamma I is a normal subgroup in gamma, and such that the intersection is trivial. Okay? Then we moreover look at an action of gamma on some K, which is co-compact and contractible. Okay, so each finite index subgroup, gamma I, acts the same way. It is co-compact, the space K is still contractible, so that you can consider the Betti numbers of what? K mod gamma I. You take the quotient. Okay? Since the finite index subgroups, the index becomes larger and larger, you may remember the Schreier formula for free groups. You may know it. And if you think in that, you know that the right normalization is dividing by the index. Okay? And the claim is that this sequence converges. Okay? And the limit is identified. It's the well-known, it's the L2 Betti number of the group. Okay? So, this explains. I must mention that the group I'm interested in, UT-FN, is residually finite. It admits such a sequence of finite index subgroup, blah, blah, blah. Okay? And thus, if you know that this is non-zero, then you know that this should be non-zero and grow linearly. Okay? This is the explanation for the corollary I gave you. And now let me switch to L2 homology. Okay, so the L2 homology is defined in a similar way to the usual homology. You have a simplicial complex. Instead of considering a vector space, you consider a Hilbert space. Okay? Which means that the generic set or space of chains, now we have L simplicial complex, and you have chains in dimension 0, 1, and so on. But not just chains, L2 chains. Okay, so what is, for instance, CK2 of L? This is the space of formal combinations, A sigma sigma, or A sigma in, let's say, R or C, or Q, and sum of A sigma square is finite. Okay? And sigma, of course, are elements of dimension K, the complex. Is it okay? So it is a Hilbert space with Hilbert base, the simplices of dimension k. Okay. So again, I want to consider the boundary map. It is defined on the base of my Hilbert space. Here you have to be a little bit careful because you cannot always extend continuously. But in our context, where we have behind, is it L or K? L, okay. Where we have an action of the group, which is co-compact. So this implies some local finiteness, and everything works well. So that I have now the boundary maps, also defined in the L2 context, in the Hilbert space context, and we define the L2 homology. What is the L2 homology? The defect of the image to be the kernel. Okay? So H, K, with a 2 of L. Oops, 15 minutes left. It's just the kernel of decay in this context. I could add small 2's here, but okay. Put it. Divided by the image of the preceding one, right? The only thing is that, you know, in the Hilbert space context, the image of a continuous map is not necessarily closed. But this quotient by a non-closed space could be really ugly. For this reason, we usually take the closure and add here a small bar. This is the reduced L2 homology. Okay? So, I do not discuss the dimension, the von Neumann dimension, but this is hidden behind, in some sense. And this is the reason why I should mention the names of Atiyah. So the names of Atiyah 76 and Chiger-Gromov 86. Who studied L2 homology and L2 Betti numbers in various contexts. Okay? Now comes the proposition, the same as this one for groups. Proposition, if the action of gamma on L, so is, say, co-compact, free, and L contractible, then the homology does not depend on the particular choice of L. Okay? Good. But observe that, moreover, here on L, we have the action of the group. The group permutes the elements of the Hilbert base. The action, thus, you get here an action of the group on these Hilbert spaces. And the action commutes with taking the boundaries, which means that in this quotient, you also have an action of gamma. So this comes with a gamma action, or a representation, if you want. A gamma representation on this Hilbert space. Okay? And this is this, which is really invariant, together with the action of gamma. Okay? And this is this, which is given a dimension using the theory of von Neumann.
Por ejemplo, un grupo te va a dar lugar a uno de estos, pero sí hay otros espacios también de este tipo que no vienen de grupos. Por ejemplo, un teorema ya un poco viejito de Solomon. Solomon estaba trabajando en la clasificación de grupos finitos simples y quería probar que no había ningún grupo simple que tuviera el mismo dosilo que este otro grupo y en el que todos los elementos de orden 2 son G conjugados. En fin, un elemento, una cosa que se quería probar en teoría de grupos, porque si hubiera existido algo así, me habría dado un nuevo grupo finito simple. Al final se probó que no había. Pero resulta que cuando uno mira la demostración de Solomon, él empieza a mirar, bueno, cuáles serían las posibles conjugaciones que podría haber ahí, y no le da ninguna contradicción. Al menos cuando mira los subgrupos cuyo orden son una potencia de 2. Pero luego, cuando empieza a considerar las conjugaciones entre subgrupos que sus órdenes son potencias de 3, ahí ya sí le da la contradicción. Entonces resultó que la contradicción no estaba en el primo 2, sino que estaba en poner los primos juntos. Y en el primo 2 de por sí, ahí sí había un objeto que estaba bien definido, y es lo que se dieron cuenta Levy y Oliver, y en el 2002 tomaron esa construcción y la mejoraron un poco para ver que esto daba lugar a un sistema de fusión abstracto, como los de antes. Y en particular, pues a un grupo 2 local finito. Y bueno, también hay otras maneras, que ya no voy a hablar, con teorías de representaciones modulares, también aparecen otro tipo de grupos 2 locales finitos. Pero bueno, para concluir, pues lo que les quiero contar es que sí ocurre lo mismo, cosas muy parecidas a lo que ocurría antes. Entonces, fíjense aquí, condiciones sobre el espacio clasificante. En el otro lado me aparecen condiciones que tienen que ver con la categoría y que son condiciones más de tipo algebraico. Entonces, sigue habiendo esta misma diferencia entre la parte homotópica y la parte algebraica. Entonces, bueno, aquí se ven varias relaciones que lo hicieron Broto, Levy y Oliver, que fueron los que inicialmente introdujeron este concepto de grupo P local finito. Y bueno, solo por darles algo que yo también aparezco, algunas de las propiedades parecidas en las que yo he trabajado, algunas de ellas, por ejemplo, con Noé, también de acá de México, en el que, por ejemplo, podemos expresar la K-teoría del espacio clasificante en términos de representaciones de este sistema de fusión o otros ejemplos, ¿no? Parecidos a los de antes. Si se fijan, muchos de ellos son generalizaciones de los de antes. Por ejemplo, este penilpotencia es una generalización natural de la penilpotencia de grupos. Y bueno, solo para concretar, para terminar, es muy interesante esto de las P locales. Una de las conjeturas abiertas en topología, y que una conjetura muy bonita desde mi punto de vista, tiene que ver con esta propiedad P local de tener un P subgrupo normal no trivial. Entonces, Quillen propuso esto en 1978, que G tiene un P subgrupo normal no trivial si, solo si, la realización geométrica del conjunto ordenado de P subgrupos no triviales de G es contraria del álgebra y el espacio topológico. Ok, voy a parar aquí.
Una situación cómoda de las dos charlas.
But just to mention, I won't say too much about that. The kth L2 Betti number of gamma is defined as a certain kind of dimension taken taking the action of gamma into account of this Hilbert space with an action of gamma. Okay? Good. And what if the action is not co-compact? And this is in some sense part of the work of Chigger and Gromov in order to define L2 Betti numbers for all groups. You need to consider it is known that, for instance, finite groups do not admit nice spaces, co-compact and blah, blah, blah. Okay? And indeed, most of the groups do not admit such a nice classifying space. Okay, so what when L is not co-compact? Co-compact. So for instance, if I consider a subgroup of my favorite group, but a subgroup of infinite index, a very small subgroup in ut Fn. Ut Fn acts on the spine, Kn. So lambda also acts on Kn. But this is no more co-compact. Okay? And so, in this situation, so this is contractible. Not lambda co-compact. And in this context, what you obtain as a homology does depend on L. But there is something which does not depend on it, which was considered by Chigger and Gromov. So it is the following. So you have your group acting on L. It is not co-compact, but it is free. So what you can do, so this means that in certain dimensions, you have infinitely many orbits. So what you can do is write your space L as an increasing union of subspaces which are lambda invariant and co-compact. It's very easy. You just choose finitely many orbits and more and more and more, and you exhaust your space like that. Okay? So you choose. So let's say L1, L2, Li, Li plus j, an increasing union of lambda invariant, lambda co-compact subspaces, right? And now what you get, you see you have more and more cells in each dimension. You have more and more elements in your Hilbert basis. And so this induces maps from CK to the Hilbert space with base the k-dimensional cells of Li. This is a subspace in a very natural manner of the same for Li plus j. And this inclusion commutes with boundaries. Okay? This implies what? A map between H of Li into H of Li plus G. And some indices, hop, hop, hop. Is it okay? Since this commutes with boundary, this means that this sends kernel images to images and so on. So this induces a map or homology. Okay. And now what you do is you consider this sequence of maps. And what HK2Li. No, let me write it on the right. HK2Li to HK2Li plus J. And then you consider first of all the image in this. And indeed the closure of the image. Then you take the limit when J tends to infinity. So you fix I, small co-compact, subcomplex, and you take larger and larger, and you look at the images, and then you let I tend to infinity. Okay? And this, and its dimension, its von Neumann dimension, will become an invariant of the group. Okay? Now observe what happens in top dimension. So in top dimension, it means that you stop here at dimension D. So what is the homology in top dimension? You have nothing coming from here. It is just the kernel of Dn, of the dd. Okay? And observe that when you enlarge your complex, so let me write it again, HK, HD in top dimension of Li is just the kernel of D. Right? And this, or Li, injects in the kernel for Li plus G. And this injects forever. Okay? Good. Now, everything also is contained in the end in the kernel of dd of the whole L. Okay? Good. Now look, if I have a subgroup, lambda, for which I know that the L2 homology is not 0 in top dimension, this means that for a large enough I, this is non-zero. And since this is a sequence of inclusions, this is non-zero. We proved the theorem. If we have lambda in gamma such that the homology of lambda is non-zero for D, and D equals the geometric dimension of gamma, then the same holds for gamma, that the L2 Betty numbers are non-zero for the ambient group. Okay? And so now you know what we have to do. Just find the right lambda. And it cannot be Z to the 2n minus 3, because all the L2 Betty numbers are 0 for such a group. But we have a kind of a relative of this, which is of this form. And I will explain you this group, and this will be the conclusion. Okay? So this group, first of all, here you have how many? 2n minus 4 copies plus 1. So here for the free group, the first L2 Betty number is non-zero. By Q-net formula, in this dimension, this is non-zero for the direct product. And then you have a small argument using Euler characteristic. And probably a theorem of Luc. And you conclude that in top dimension, 2n minus 3, this is non-zero. And what is the group? Well, first of all, you pick this L2, this F2, inside out F2. But the subgroup generated by X1 and X2. It is known that these groups, so this is, I told you, this is isomorphic to GL2Z. It is known to contain subgroups which are free on two generators, right? You put it back to out. To out of the group generated by X1, X2. Okay? And then you pick an alpha here, an automorphism on these two generators. And you define your automorphism this way. X1 is sent to alpha X1. Okay? The automorphism acts on the group generated by X1, X2. X2 is sent to alpha X2. Okay? And then X3 is sent to some element L2 times X3 times R2. And now this L2, R2, and so on, they all belong to the free group generated by X1, X2. Pom, 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 X, let me continue here maybe, Xn sent to Ln, Xn, Rn. You see, I multiply, so I keep this subgroup globally fixed, but acted upon by an element of the automorphism group. Excuse me? I'm sorry. L3, R3 again. L3, R3, L4, R4, pom pom pom, Ln, Rn. So all these elements belong to the free group generated by the first two generators. You multiply on the left, resp on the right. They are used generators. And so you see you have a copy of F2 acting by left multiplication, right multiplication, and so on. And these copies commute. This gives the direct product of the F2s. Okay? And the alpha just twists these elements. Okay? So the action here is induced by when you pick an alpha here, you act on each copy. Okay? And so this is a subgroup, lambda, for which it is easy to see that you have a non-zero L2 Betty number in top dimension. And by this, easy reasoning, you get that the L2 homology is non-zero for ut Fn. Maybe I stop here.